Hi everyone. Repair reliability seems to be a really big thing right now, and there's many factors behind it, and it can really make or break any business or any serviceman or technician. If you're designing something, it can break the engineer as well, or even the company, depending on how badly the device is designed. So there are a few very simple things that you can remember that will make your repairs or your designs last longer. So the first thing that we're going to talk about is a thing called mechanical stress, and I'll get things set up here and I'll give you an example. Mechanical stress plays a big part in device failure, and in an amplifier like this here, they've assembled it in a way that they've kind of gotten around that. So what I'm talking about is the output devices here. So this is a large MOSFET stereo power amplifier. There's basically two separate, almost mono-type amplifiers in one case. They have two power transformers in the back. You can see this here is two power transformers. So basically just two separate amps in one case. And what they've done here is they've installed the circuit board. They've fastened the output devices to the heatsink, so they're just floating on the heatsink with the legs just kind of sticking out like that. They put everything all together, and then in the end, somebody has to manually come in and then bend those leads. The circuit board is actually notched, so they have to bend the leads like this on the underside of the board and then solder them. Now, this is the proper way to do things, and that's the reason that these amplifiers here very rarely ever fail. The only thing that goes wrong with them is they go out of bias, and sometimes the caps fail in them. But I have never come across one of these amplifiers here. They're made by Fisher, and LXI is another brand name that they put on it and all that. I think LXI was a Sears brand way back in the day. It's the same amplifier inside. They just never fail. And it's a good thing too, because if any of these output devices go at this point, that's pretty expensive considering these are N and P channel FETs right here as the output device. At any rate, so back to this. So they've screwed the device to the sink, and then the very last thing they've done is soldered the device in. Very, very good assembly technique. Now, what I see a lot nowadays, and this drives me up the wall, okay? I see, just like you, I go around on YouTube and I watch other repairmen do repairs on car stereo power amplifiers, power supplies, big stereo amplifiers like this. And one of the big things is in the car stereo amplifiers, you'll have rows of just output devices. And what they do is they've got a piece of silicone heat thermal. It's basically a thermal transfer pad. And it insulates the devices from the heatsink as well. And what they do is they have this clamp, and it holds down a whole bunch of these transistors onto a heatsink at the same time. And the leads from the devices, the devices are bent over from the circuit board. And the leads from the devices themselves are soldered through plated through holes. So what they're doing, what I see so many technicians do, and I watch this all the time, and it's just, I don't know, instant loss of respect for the repairman when I see this. Everything's going well, and then I see them do this, and it's like, oh, here we go again. So what ends up happening is when they bend the device over and it's soldered in place, that if you have a device like this and you bend it a bit, you can see how it always wants to come back, right? You see how it always is just trying to come back. And it goes for anything, transistors and all that kind of stuff. You have a bit of springy like tension there, right? So now if you solder the device into the circuit board first and then bend it, the device is going to want to lift a little bit, right? Well, that's mechanical stress on the solder joints, and it's continually sitting like that. And not only that, when you tighten it down to the heatsink, it's not only pulling the device down, but it's also putting down force on those legs of the transistor, so it wants to crater the solder joints in the plated through holes. That's such a big no-no. Whenever you replace an output device in any amplifier or power supply or anything, you mount the devices to the heatsink. If needed, you stick the leads through the plated through holes without soldering them. Bend the device over or pre-bend the legs. Clamp them down to the heatsink. So put everything back together so everything is going to sit in place as it would when the unit is in service. At that point, when you're done and everything is screwed down and tight, then you add solder to the joints. Solder the transistors in. If they're plated through holes, you can solder them from either side of the circuit board, no problems. And with a little bit of finesse, you're not going to have a big solder ball floating on the bottom side of the circuit board. Feed just enough solder in from the top side, and you will get through that. Those devices, the solder joints will never crater at all. And the device itself won't have that mechanical stress on it. The circuit board won't have mechanical stress on it. You'll create dependability just through that alone. In fact, traces don't lift and all sorts of nice things, you get from doing the job right. I've watched companies put together amplifiers on the assembly line, and all of them are measured up and soldered in place, and they just batch bend them over and clamp them down, and it goes down the line. And then they wonder why their amplifiers fail in a year from thermal cycling. So that's a huge, huge issue. So if you can remember that, that'll make your repair that much more dependable, and of course establish quite a reputation for you as well, because your device won't come back in for repair, at least for that anyways. So what you want to do is install all the devices first. If you want, pre-bend the leads, clamp them down to the sink so that the leads are going through the holes, but nothing is soldered. Get everything put together, and then the very last thing is solder the device in place. Here's something really interesting that I've heard quite common lately, and I've seen this in comment sections on YouTube, and I've had the comment myself as well. People say to me, Paul, you're using too much thermal transfer compound. You shouldn't use that much. That's the silliest thing I've ever heard. What you do is you put thermal transfer compound on the back of the device, a nice thick layer of it. And then on the mica spacer that's going to be on the heatsink here, you take the mica spacer and smear a nice thick layer on that as well. And then what you do is you tighten the device down, and what it does is it squishes all the excess paste out, and you wipe it off. And that way you know that you have a nice thick layer on each side, and the thermal transfer is going to be really good. Now, I've seen so many people put it looks like a fingerprint of thermal transfer compound right in the center of the device, and then they put just a little fingerprint of the compound on the other side of the mica spacer. That's not the right way to do things. You make sure this is assembled properly. These amplifiers are such a good example of good assembly. That's again the reason that these things last. Look at this. Look at this. They even put this on the leads of the resistors. You'd have nice little ceramic legs on the resistors. This thing just reeks of good assembly technique. Anyways. You can see on this, that there's a nice even amount of thermal transfer paste. You can see the little ridge gets squishing out just a little bit there. Well, what they do is they tighten these things down, and it's very simple. Just run a Q-tip around the device, and then once you've got the bulk of it off, the stuff that's squished out, get an alcohol wetted Q-tip and go around the device one more time, and you'll have a very, very clean assembly with a very even amount of thermal transfer compound around the mica spacer, from the mica spacer to the sink, and then from the device itself to the mica spacer. That is extremely important. Even though the die is sitting, right in the center of the device, it still is transferring heat to this entire pad. You want that entire pad to have the most thermal transfer, or the best thermal transfer it can have, so it can get rid of that heat into the heatsink. So if you've ever come across a device, you say you've removed, I find this very commonly in power supplies, you remove a switch mode type, a switching FET or switching transistor, or if you're working on a power supply, you remove a pass element like a 2N, say 3055, 2N 3055, or 3771 or 3772. You remove one of them, you look on the underside, and you see just a little fingerprint of thermal grease right in the center. What about the rest of the whole, TO3 style transistor? What about the rest of it? Is it just the center going to have that thermal transfer? You want the whole thing caked with it. Thermal transfer compound is cheap. It wasn't way back when, and this may be the reason that they did that. But nowadays, thermal transfer compound is cheap, and it's really good insurance to make sure that the device isn't going to come back through a failed output because it couldn't get rid of the heat properly. So something to keep in mind. You can never put too much of that paste on here. The worst that's going to happen is you tighten the thing down and it's just going to squish out. That's it. Just wipe the stuff off and move on. That's it. So better to have more than to have less. When working on point-to-point wiring and things like that, you'll see in a lot of the manuals, this was very common in the old Heathkit manuals. They would show you how to wire things. So they would, put the wires through like this, and then they would, have you fold them around like so. And move this one up here and do the same thing to it. Like so, right? And then they would tell you to solder just that area. Okay, so all they want is just a touch of solder on this. So you would see the solder joining the wires to the terminal tie strip, but you wouldn't see, like, the actual hole wouldn't be filled or anything. Basically, just enough solder just to solder it to the terminal tie strip. Well, I kind of frown upon that. I whenever I'm working on any of this kind of stuff, I always fill the entire hole full. Now, unless I'm going to add wiring to it, until the very end, I'll just tack it in place, just so that I can move this around, and it holds the loops in place and doesn't move this around. Now, that's another part that can, very easily, I guess you could say, through mechanical stress, the solder could break. Even though there's still play when you bend the leads around, right? There's still play in there. And if you just solder, just the actual area itself, the little eyelets, which are the little ears, I should say, if you just solder the little ears to the terminal tie strip and leave the rest of it open, if you move the resistor once or twice, there's a good chance that you're going to open that solder connection. Whereas if you fill the entire little hole on the top with solder, you have no chance of that. Now, I've only seen, really, I guess a few different construction manuals suggest that. So mostly the kit types, and maybe it's because of the supplied solder. Maybe they wanted you to be, frugal with the solder or something like that. I really don't know. But just another idea to make things a bit more dependable. Now, as I've said before, I'll repeat this again, there's no reason to actually have to fold this around there. You can poke the wires through and just leave them like that, so you don't need to do this at all. So I'll just turn this around here and grab this one here and turn it around too. So there's no reason to actually fold those. You can just stick the wires through if you want. So we'll just ignore that in because that looks kind of ugly now. So you just stick the wires through like so, and then just fill the actual hole and solder it like that. So if I could actually get this thing to stand up properly here. So yeah, just stick them through the hole and solder it like that. Now, if it's a resistor that's going to generate a lot of heat, and that particular point I'll curl it around just because it's a little bit better, because again, you're dealing with expansion and contraction through heat continually. But a lot of the test equipment companies did just this and solder it all the time. That's what they ever did. I've never come across a bad solder connection because of it. So a little bit of a tail there. Oh, you need to bend the leads around. Another neat little construction tip is if you're using terminal tie strips like this, you'll notice that there's little holes in the bottom. It's where they crimp it onto the little fiber board here. Usually what I do to keep things really clean is I run the wires along the chassis, and I'll solder the wiring into these little eyelets at the bottom, right where they've crimped it in here, and then I leave the top for the components. And that keeps the wires on the chassis, and it allows the components to be above. It makes a really clean construction. Just a little tip there if you're ever doing that. So yeah, you know what? Don't spare on the solder. You don't need to. The stuff is plentiful nowadays, and you don't need to add just a little bit of solder where you've bent it around. There's no point. Fill the whole eyelet full, and things will be much more dependable, and you won't have to service it for a very long period of time. Now, I plan on doing a video as well here in the future, and you can leave your comments on this below if you'd like to see this. Is a video basically just explaining when you want to accept a job for repair or pass it on. Now, there's a lot of, I have quite a few examples that I can show you of a job that you could take and a job that you should pass on. And I'll just back this out here. So the whole gist of it would be to make the proper decision if you're in a business, in a repair business. Taking on business from a customer that doesn't want to have you do the job fully can affect your reputation. So I'll give you an example. So you open up an amplifier and the thing needs to be recapped completely. And the customer says, I only want you to replace the failed components. And the customer says, I'll pay you, and he's offering you a decent amount of money to do that, just to replace that. But he doesn't want to do the job in its entirety. A lot of the times when you get a job like that, you should pass on it. Don't actually take it, because if you see the other components and you know that they're going to fail in a short period of time, it always happens. The customer, even though he told you only replace the parts that are bad, when it fails, it'll become your fault. That's the way it always happens, over and over and over again, unless you know the person, or maybe you're very good friends with them. Who knows? Sometimes even if you're very good friends with them, who knows? But that's the way it always seems to go down. So you have to be very careful about making decisions with jobs if you're a repairman. Now, I have lots of different examples that I could show for that, and a lot of them are still at the old lab. I could bring some of them over here. They're basically things that need to be completely repaired in order to be dependable now. And some of them are just, you just need to replace a component or two and it should be fine. So I can show you how to differentiate between the two. So if you're in business, you don't sink yourself. Now, believe it or not, that really is a huge thing in the repair business. Word travels fast, and if you repair something and it dies in a week and the customer gave you instruction to only replace those parts, again, it usually always ends up making you look like the dirty shirt. So I have lots of examples of that I can share and show you what to do and what not to do. If you're interested in seeing a video on that, you can leave that in the comments below as well. All right, I hope you found this video beneficial, and I will talk to you next time. Bye for now.